few days ago. All right, let's see. Thermal efficiency. Let's talk about that. Thermal efficiency. I'm going to alarm anybody, but not this isn't working. There we go. Quit again. Thermal efficiency can be computed as follows. All right, let's see. It is indicated efficiency. Indicated thermal efficiency. Equals, I'll put it down here. Indicated thermal efficiency equals indicated horsepower or indicated horsepower, IHP, times 33,000, and that number will make sense as we move through this class, divided by weight of fuel burned, divided by minutes times heat value times 778. All right, so how does that work? So if the indicated horsepower equals 85, so I have a little C85 Continental, 85 horsepower. Let me see if it's...
Kevin?
Yeah.
Is that weight of fuel burn divided by minutes and then
yeah.
multiply all that?
Yeah,
okay.
like that. So indicator, if an 85 horsepower, I wrote this bad, so I have to think about it. If an 85 horsepower engine uses 50 pounds per hour,
calculators. Oh, shit.
and the fuel has a heat rating, heat rating of 18,800 BTU per pound. Then how do we figure this? Well, let's figure out how much fuel we burned. So weight of fuel burned per minute. Per minute. So that would be, how much fuel do we burn?
50 pounds per hour.
50 pounds per hour. We want to figure out how much you burn per minute, so we would divide by 60, which would equal
0.833.
0.833 pounds. All right, so plug that all in. So we have indicated horsepower is 85 times the constant, 33,000, divided by weight of fuel burned per minute, which is 0.833, times my heat value, which is 18,800, times a constant of 778. So we would end up with, big S number 2805000 divided by 12184,569. Divide those two, we would get 0.23, which is the same thing. Convert that to percent.
23%.
So 23%. So that little Continental 85 engine is 23% efficient. Well, then I thought, well, that was fun. I wonder what my 0470 does. Let's see if I did this right.
Is that the one in your plate?
Yeah,
Over 10.
so I have an 0470. So it's my 0470. So it's an 0470 uniform to be exact, in the Cessna 182. I looked at my pilot operating handbook, the POH, and at 10,000 feet, I burn 11 gallons per hour, which would be how many pounds? Okay, that's 66 pounds. Because remember, it's 6 pounds per gallon. So I have 66 pounds. And that's at 64% power. 64% of power. My max power is 230 horsepower. So, all right, so let me see. We're getting interrupted with doing that. So how much power is that then? What's my power? I need to bring in my, so it's 64%
Oh, 66.
of 230. So if my max horsepower is 230, but I'm saying, nope, I'm cruising along at 10,000 feet at 64% power,
147.2.
147.2, so 147.2 horsepowers. Follow?
Wow.
So I'm trying to figure out how efficient my engine is. So I looked at the pilot operating handbook. 10,000 feet tells me I burn 11 gallons per hour. How accurate is that? Dead freaking accurate. It's insane. I have a fuel flow meter and I go up to 10,000 feet, lean it for right how it tells me to lean it. I look at my gallons per hour and it's like 11.2. I'm like, damn. All right, it's 10,000 feet, burned 11 gallons per hour. It's also 66 pounds at 64% of the max horsepower. So I'm at 147.2 horsepower. So let me see. What is the formula then? We want indicated horsepower. Let me see. Go back up here. Indicated horsepower times 33,000. That is 147.2 is my indicated horsepower times the constant, 33,000, divided by how much fuel I burn per minute. That would be
1.1.
66 divided by 60. That answer times the fuel, because we're using the same fuel we used a little bit ago, whatever they, times 778. So 66 divided by 60 is 1.1 times that. We'll just keep this simple. We ended up at 4857600. I may have made a typo here, I'm not sure. 16, did I miss a 0? 089040. I either missed a 0 or put the comma in the wrong spot. I don't know. Did anybody do that? What does it come out to be?
You're right.
This is right there?
Yeah.
Okay.
4,800,000.
That's it. There we go. Which equals what percent? I heard it. About
Divided by
1608040.
30%. 0.301.
Yeah. 0.3019. 30%.
30.2%. Woohoo!
It's above average.
Yeah.
That's at the top end of the 20 to 30.
Yeah, I know.
That's
Oh,
good.
lucky me. All right, so that's how we come up with those numbers. So what's the takeaway? Engines are about
20 to 30%.
20-30% efficient as far as extracting the heat energy from the fuel. Where does all the other heat go? So 30% goes to pushing the piston down. 5 to 10 goes to friction. 40-45 out the exhaust, and whatever was left, 20-30 is heat radiation from the cylinders. So the heating of the cylinders, the exhaust going out, the heat going out the exhaust pipe, all wasted. What do we have to try and recoup some of this wasted heat? What can we do?
Turbocharger.
Let's start with my wife's favorite thing. What do?
More gas.
We heat the cabin.
Oh, yeah.
All right. Yes, we had a turbocharger. Turbocharger is, in theory, takes the heat energy, extracts the heat energy from the exhaust. And it does that, puts a little back pressure on the engine, so it takes a little bit of power away from the engine. But otherwise, it's, in theory, a free lunch there, where it extracts the heat energy from the exhaust to drive a turbine wheel. Yeah.
EGR valve?
No, it's terrible. I don't think that helps at all. EGR valve, if I'm not mistaken, just in a car, not an airplane, you'd never do this in an airplane, simply takes the exhaust gas and it puts it back in the intake, which was acceptable, huh?
Yes, it does. I have one.
Which is acceptable until we had direct injection engines. Now there's nothing to clean the intake pipes, so it all gums up. And so, all right, let's see. Volumetric efficiency. And valve overlap. All right, talk about the word aspirated. If you're talking in medical terms, it's a very bad thing. It means you just inhaled your own sick and probably died because you were drunk. All right. But in engines, we talk about aspiration. We have normally aspirated engine would mean that there's no turbocharger, supercharger, or anything to force the air into the intake side of the cylinder. So we can go over to. There we go. Good. Still running. I wonder how many gallons per hour I'm burning over here. So here's the intake side of things, and there's nothing pushing it in. It's just simply the difference in air pressure between when the piston comes down. There we go. Stop. When the piston comes down, it creates low pressure inside of here, and because there's high pressure out here, the fuel and air mixture just naturally would want to go into this cylinder. Now, if I had this engine and I stopped it just like this, the pressure inside the cylinder would equal the pressure outside the cylinder because there's more than enough time for it to equalize. Yes?
Yeah.
But it isn't that way. It runs much faster. And so when it's running faster, as the that's just obnoxious. I shouldn't have. As it's running faster, right? As that piston comes down, but it's running fast, it doesn't have time for the fuel-air mixture to completely rush into the cylinder, go through the intake valve, and fill it up to 100%. So at some point, that intake valve is going to close off and say, you've had enough time, we're going the other way. And if we were to stop it right there and measure it, see, power, exhaust, intake, back it up a little bit. Right there, it's all rushing in, and then the very next frame, boom, closed. And piston's going the other way. Well, what happened is that fuel and air didn't have enough time to get in there. So if we measured the difference between the two, and we'll say this engine is running wide open throttle, right? A throttle is literally a plate, a throttle plate that restricts the air coming in, so we have idle, so it runs slow, run faster, 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 wide open, okay? So when you mash your foot down on your accelerator in your car, that opens the throttle plate perfectly wide open through a tube. Instead of blocking it off, it's wide open. And if we were to measure the difference between the two, we would find that if the outside air is at 30 inches of mercury, which is a standard A, be 29.92, around up to 30 inches, best case scenario, you're going to be missing an inch, about 29 inches of manifold pressure. So that cylinder is not going to fill up all of the way. And if we were to make the valve smaller and smaller and smaller, it get worse and worse and worse. So we're trying to get as much air, outside air, to the inside of the cylinder. That's called volumetric efficiency. And things that hurt volumetric efficiency would be a lot of tubes, a lot of bends and elbows in the air induction system coming in to that, a dirty air filter, small valves, valves that didn't open all of the way, valves that closed too early, valves that opened late. So all of these things can hurt it. Things that can help. Putting your induction filter facing forward. When I was a kid, I was really cool. I had a Z28 with, what was the 82 Z28? It had an underwhelming 200, I think it had like 190 horsepower or something. Had the 302. You know those. What is that? 302 or 305? They put 305. Ford's the 302, right?
Yeah.
Yeah, so that 305.
302, but it was built from 67 to 69 and built as a performance engine.
No, this was not performance.
Yeah.
So the 82 Z28 had,
At the other end.
but it did have one cool feature, and then it had these louvers on the hood, and when you floored it, vacuum operated it, it would open up and would allow, I think it bypassed the air filters now I think about it, air to be forced down into the engine, which kind of act like its own little turbocharger, if you will. I don't know. So forced induction. So in aircraft, we do that. We face the air intake forward behind the propeller, so the propeller pushes air in. So that helps kind of push that. Getting rid of the elbows, clean air filters, opening up the intake valve a little earlier than what you see here, closing it a little bit later than what you see here. These are how we can increase the volumetric efficiency. So volumetric efficiency is important. If we get into turbochargers or superchargers, no thank you, then what happens is they're actually forcing air in. You actually are installing a compressor that takes air and compresses this intake tube way, I shouldn't say that. It compresses that and forces air in. There's different ways to do it. We'll cover turbochargers next class. So, volumetric efficiency and valve overlap. Number one, volumetric efficiency, and I don't want to keep writing that, so we'll put VE, volumetric efficiency, VE, is how efficient a cylinder is at filling up to capacity while operating. So, right, my airplane has a 470 cubic inch engine, which means that if you were to fill a cylinder up full of a liquid while it's at bottom dead center and then push that cylinder forward till it was the top dead center and measured how much liquid came out, and you said, okay, there's that much liquid, and how many cylinders are there? There's 6. Multiply that times 6, you'd end up with 470 cubic inches. Well, that's how much air should then be sucked into it, but how much air really goes into it? Well, if it was 470, it would get X number of horsepower, but if it's really only about 400, I mean, missing a bunch of horsepower. If it's 200, I mean, like, you know, that's a lot of horsepower loss. So you want to get that air into there. Let's see, feeling operating. Okay, that's it. And I say while operating because obviously when the engine is sitting still, well, like the thing was, then it will equalize, and that doesn't count. So volumetric efficiency of a normally aspirated, which means what?
Swallowing your own vomit?
No.
Oh, sorry.
Normally aspirated means it's not
Forced.
forced. It's not turbocharged or supercharged. A normally aspirated engine is always, all the time, less than 100%. Oh, they try, but you just can't get 100% of the air that fits in that cylinder into it because it's just moving too fast. It only spends so much time going down, and the valve's got to close. It's turned on going the other way, and the air just doesn't move that fast. The slower you move the engine, the higher the efficiency would be because this piston is moving slower. Air has more time to go in there, but as you increase RPM, you're going to lose some of your volumetric efficiency. Except volumetric efficiency, except, that is true what I said, except it's completely false because while it's moving slower, and you could allow more air into there. Let's back up and go back to the throttle plate, which is closed, not allowing any air to come in past the throttle plate. So the piston pulls down, and it's got this very tiny little opening down here, so it doesn't draw anything in. And that's where we get a big vacuum inside of our manifold pressure. Our manifold has a vacuum. So that is to say that, if you go back to old cars that used a lot of vacuum-operated stuff, Mercedes at one point used vacuum-operated door locks. Which car was it used vacuum-operated? Was it Jeep or something? Used vacuum-operated windshield wipers, and a whole bunch of stuff. So anyway, the vacuum came from this idea that the fact that the throttle plate is closed, the piston moved down, and it's just like a syringe, because you guys are big drug users. Because you have fish tanks and stuff. You put your finger on the end of the syringe and you pull it back. What happens? You let go. Pow, goes back the other way, right? You're like, I don't play syringes. Why do you play syringes, Kevin?
Sure, yeah.
All right, so yeah, if you got a syringe and you block the end and you pull it back, you just create this big vacuum in there. Well, it's the same thing with an engine. You you close the throttle, you're at idle, piston goes down, it tries to suck on something, there's nothing to do. So in the whole pipe that goes, the pipe that goes right here is going to have a big vacuum on it. Because this came down, it was trying to suck air out, but this throttle valve's closed, so it didn't work, so you got a big vacuum. So that is why engines would be less thermally efficient, even though it's going slower and down. So at idle, you have a much higher vacuum, or we say a lower manifold pressure. At high throttle settings, you would lose your vacuum. But in aviation, we say you have a higher manifold pressure. And the point I was making is volumetric efficiency is greater at wide open throttle because the throttle is open. You have less restrictions. And conversely, that would be volumetric efficiency is less at idle because throttle is closed. Let me see, we'll say sharp bends in induction reduce efficiency. And high air intake air temps reduce efficiency. Because the air is hot, and so it's less dense, so it tends to reduce efficiency. All right, so we got to increase our efficiency. We got this model over here running, this thing going around, and this is not a very efficient engine. Not by a long shot. Oh, it would work, but we could get so much more power out of this if we just did a couple of little things. And what are those little things we got to do? What's that? Yep, bigger valves. Number one, bigger valves. Well, okay, so how do you get bigger valves? Well, you make them bigger. What else do they do? Multiple. We don't do that in aviation that I'm aware of. I've never seen that in any of the legacy engines. They just have a big intake valve, a smaller exhaust valve. which we'll talk about later. But your cars, more modern cars, they have, 16 valves per, I was going to say per cylinder. No, per engine. That'd be a 4-cylinder engine. Have 4 valves. They do 4 valves now? Yeah. What do you have, the Subaru? What does that have?
It's a 4-cylinder. I'm gonna say it's a 16 valve.
Probably overhead cam. All right, to increase volumetric efficiency, valves open and close. Valves open and close at times other than BDC and TDC. Mostly. Not everything works that way, but for the most part. Right? Because the little animation we had, they always fully closed, fully opened right there at top dead center. Well, number one, they don't fully open and close that fast. They're on a ramp, so they got to move open and move closed. You didn't really see that so much with the little drawing, but it does it at times other than that. So we got some terms here. Valve lag. That is opens or closing. Opens or close. Opening or closing. Let's keep it consistent. Opening or closing. I like that better. After TDC or BDC. In other words, late. Valve lag is something that happens a little late. Valve lead, let's say opening or closing early. That makes more sense. Other than TDC or BDC, so that'll be earlier before that. And this term right here, which is a hard one to remember, but you do have to remember it. Duration is time valve is off its seat. Off its seat. Open, which is to say open. That's duration. Let me know when you got caught up. All right.
No, I'm not.
Well, why didn't you say so? It's like I just did.
You're good.
All right. All right, this is out of your book. And to be fully honest with you, this makes no sense to me. I cannot make heads or tails of this, even though I know exactly what they're trying to say and I can understand the entire concept. I look at that and go, what? And I've spent a lot of time trying to figure it out. How do I explain that? And then one day I'm like, oh, just don't draw it like that. Then it becomes real simple. And so it's like this. What they are saying is this. I'll try and make it somewhat neat. What they're saying is this. You have an engine. And I'm going to make it like this. We'll have intake. What comes next? Intake. Compression. Power. Exhaust. Okay. And if we look at this and say, okay, each one of these is an event. I need more room. Forgive me for 1 second. This will make more sense if I give myself just a little bit more room. Here we go. Intake, compression, power, exhaust. What comes next?
Same thing. Intake.
Intake. What came before it?
Exhaust.
Exhaust. There we go. So now we can kind of look before and after, because that's what's really happening in life. It's not just isolated to these 4 things. And so I've got a bunch of things happening. Okay. For the intake stroke, which way is piston going?
Down.
Down. Okay, so it goes down. Where compression stroke goes up. Power down. Exhaust up. Intake down. That means this one's got to go down. All right, so we see what's happening here. See what's happening? I got that. I drew a representation of what's happening here. I've got an intake, exhaust, compression.
Your first exhaust.
Oops, sorry.
It's second exhaust.
I was like, okay, now I'm lost.
There. Okay, so here we go. We've got cylinder, and we've got the piston. Piston goes up, pushes the exhaust out. Comes down, sucks it in. Goes up, compression, power, comes down, exhaust goes back up. That's what I drew right there. Okay, just instead of going in a circle like they did, I did it like this. Now, what they're saying is that the intake valve, well, we know this. We'll say what we know. The intake valve is open during which stroke? Intake. Okay, so here we'll use blue and we'll put the intake valve right there. Intake. So intake, and back over here we got the intake valve. That should be open, right? Okay, and the exhaust, I should use red, save my red. Exhaust is going to be open during the
Exhaust.
okay, so let's say it's open during the exhaust stroke, and power to the exhaust stroke. Okay, so if we basically took the little animation that we've been watching, this is what's happening, yeah?
Yes.
Okay, exhaust valve, exhaust right here. This is the exhaust. Exhaust valve, this is the exhaust valve, is open. Exhaust valve is open. And then it closes, and then right away this opens, so this is the intake valve opens. And over here the intake valve opens. But it doesn't happen like that. If we go back to this drawing that was in your book, it says that the intake valve opens 50 degrees before the piston reaches top dead center. So the intake valve opens 50 degrees, intake valve opens 50 degrees before piston reaches top dead center. Which spot is this right here? Right here, this is TDC. This is BDC. Follow? TDC, BDC. So if it's saying, this example, that the intake valve opens 50 degrees before it reaches top dead center, that means it's going to open up over here. Well, let's put this 50 degrees right there. 50 degrees. So it opens way up in there. Opens 50 degrees before piston reaches top dead center. And I'll tell you in a little bit. And it closes about 30 degrees after top dead center. So it's a little bit before, a little bit after. Well, I got to remember to do this over here, so this over here, we'll do this here. So that's 50 degrees, right? All right, so it's open longer. Well, the reason why you do that is because as this piston is coming up, and of course where I drew it on the line going up and down has no relevance to anything. I just put it there in the middle. So as the piston is coming up from exhaust, it's going up and it's pushing that exhaust out, right? Because the exhaust valve is open, so it's pushing the exhaust out, pushing the exhaust valve. Then it gets to up here, and now suddenly the intake valve opens. Well, the reason why it does that is because, we can go back to this. Okay, so, oops, we're on the exhaust, coming up on the, slow it down. We're coming up on the exhaust, exhaust, exhaust. Now right there, it's pushing the exhaust out, and you have gas flowing out. If I were to open this intake valve, it would make no sense. You'd think, well, wait a minute, the piston's coming up, so it's going to kind of push now exhaust out the intake. It doesn't. You have inertia behind that intake, which is already flowing. You have inertia from the gases going out, which tends to create a vacuum and suck it through. And so rather than closing this with a little bit of exhaust in there, this kind of helps drive out some of the exhaust as it comes in and creates much more of a cleaner environment in there, I guess, if you want to call air and fuel clean. So it pushes that out. And so you're dealing with this inertia of gases, which allows that to come in. So let's open it up early and let some of this fresh air come in, because the pressure outside is going to be higher than it is inside, even though the piston's still coming up. So, hey, let's get it in there. All right, so then we do that, and so the valve's already been opened, so now it's open, 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 but here it just closed, but with us, we're going to let it go another 30 degrees before we close it. Why? Because if you figured it out in real slow motion, the piston comes down, 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 and it stops here at bottom dead center. We haven't filled up the cylinder. It's not full. Well, you figure out, when is it full? Is it full here? Not yet. It's still not full. Right about there? Yeah. That's the point where it's as full as it's going to get, and if we left the valve open any longer, it'll start pushing it out the other way, so to speak. I'm kind of simplifying my thoughts here, but anyway, so that's why it's like, let's leave it. We could say there's more fuel and air in the cylinder now than there is here. Follow? It doesn't make sense because the space got smaller, but because it didn't fill up, we'll just leave the intake valve open a little bit longer. All right, and so then we look back here at the exhaust, and we say, oh, we haven't done exhaust yet. So exhaust valve opens about 30 degrees before bottom dead center, so that's going to come over here. Oops, wrong color. So exhaust. Well, exhaust, it's going to open early too, up into the power stroke. So we got this power stroke here, and instead of using the power, we're going to open the exhaust valve. And it's going to, and there, let me see, close about 25 degrees after. So we got to go 30 degrees that way. No, 20, then we're going to go this way, 25 degrees, and this way, 25 degrees. And this was what, 30? 30, I said, okay, 30. There we go, 30 degrees. So it's going to open early and close late. All right, so what's going on with that? Well, the thing is, we talked already about the fact that as the piston is being driven down by the expanding gases, we said the gas is already done burning by about, what, 14 degrees? It doesn't take long. It's already, the gas is burned, but it's still expanding. So we're going to get down to a point, which we'll say is about 30 degrees before it reaches bottom dead center, where I like to think of it this way. The expanding gases is already pushed on the piston. And if the piston is kind of moving at the same rate as those expanding gases, then you're really not taking advantage of these expanding gases. And because these gases are very, very hot, I'm going to say it's in the neighborhood of 1700 degrees. Because it's 70, why keep it in the cylinder? You keep the super hot gas in the cylinder that's not doing anything, and you're going to overheat the cylinder. So get it out of there. If it's done doing what you needed it to do, open the valve and get it the heck out, which is why you open it as fast as you can. So they open it much early to get that gas the heck out of there. All right, so we push it all the way out, but we're going to leave it open a little bit longer. Why did we leave it open a little bit longer? Well, this really speaks more to what I said earlier about the inertia of the gas is still flowing out. So even though the piston's going to turn around and start coming back down a little bit, we've reached intake, exhaust, we push all the way out. Now the piston's coming back down. We're going to leave it open a little bit longer. Yeah, the inertia of the gas is still going out. We have inertia of gas coming in, so it tends to want to push out that exhaust burnt gas and get it out. Continue to keep getting it out. We don't want it in the cylinder. We can't really go above 400 degrees with these cylinders. They'll start melting, and that's not real hot for. You can get 400 degrees pretty fast. So we want to get that out of there. So that's what that looks like. All right.
Valve lag and valve lead.
What?
Valve lag and valve lead.
Does that change with forced induction, like adding turbos?
Oh, it changes with all the different engines. This is just an example. We're going to talk about your engine, which doesn't even match this. They do something weird. They don't tell you. I've looked everywhere for the exact timing. In fact, somebody wrote it out for me. I had them do it as a project, and then I lost the card. But I do know some things. I want to say, off the top of my head, the Lycoming, they don't have this 50 degree here. There's no overlap that way. They have no valve overlap on the Lycoming. But I think this is more of a Continental. This is in your book. This is where this comes from. So that is this. Looks just like it, doesn't it? I think that I can't even, makes no sense to me. So I'm like, yeah, that makes perfect sense to me. But I think, Oh, yeah. I thought, oh, I could be really cool, and I don't have to draw it all out. All right. So this is the same thing that I just drew if I did my PowerPoint correctly. So I have exhaust, intake, compression, power, exhaust, intake, compression, power, right? Those are just the going across. And each one of those events is 180 degrees. All right? So if we go back to this, and we look at the crankshaft down here, that's 180, 180, 180, 180. So from bottom dead center, move it slow, to top dead center, that crankshaft right here moved 180 degrees. Yes?
Yes.
Okay. So hopefully everybody's on the same page. So for the exhaust stroke, it's 180 degrees. For the intake stroke, it's 180. So 4 strokes is how many degrees? 720. So we can start here with 0 degrees, 180, 360, 540, 720, or 0, because this is intake, compression, power, exhaust. These 4 right here make up one cycle. Thank you. That's the exact word I wanted. So it's 720 degrees. All right. Intake. Sorry, exhaust. Exhaust pushes. Intake down. Compression, power, exhaust. Intake, compression, power. Got it? All right. So the intake valve is open about 50 degrees before top dead center. And it closes about 30 degrees, we'll say exactly 30 degrees after top dead center. So we have the 15 to 30.
Is that bottom dead center?
Yes, that'd be bottom dead center because the piston is right here at that point. Okay?
Okay.
So what is the duration of the valve? Duration means
Time it's open.
time off its seat. And I tell you, this is on the test. It is part of the FA test questions. They ask you to do this. And the way I would answer this question is exactly like this. I would just draw it out and say, okay, what is the duration? Well, it's open this entire time right here. That's how many degrees?
180.
180. And it was open 50 before and 30 after, so it's just simple math. 50 before, 180 plus 30. So it's open
260.
260. I did it twice in case you need to see it again. Can we do it again? Sure, it's right over here. So to the right. So it's open 50 degrees before. It's open the whole time, which is 180, and 30 after. Therefore, it's 260. All right, let's do the exhaust. So the exhaust is open, the entire exhaust, which is how many degrees? 180. It is 30 before and 25 after, so 30 plus 180 plus 25 is 235 is the duration. Now, we have a thing called valve overlap, which means both valves are open at the same time. How many degrees of valve overlap do we have?
Both valves open.
Well, you can look at it right here. They're both open, or right here they're both open.
25.
So the intake is open how many degrees early?
30. 50.
50. And the exhaust is open how many degrees late?
25.
So 50 plus 25,
75.
75 degree overlap. 50 before, 25 after.
Interesting.
All right, you should be able to do that. It is on the test. And it isn't like one thing. It's like several questions, I think. Like question 1 is, what is the duration of the intake? Question 2, what is the... So it's going to make up like 5 different questions right there. But that's not hard, right? What do you do?
Draw it out.
Draw it out. Just draw a graph. I don't think I have like another... Yeah, I think I do. So, all right. So we'll talk about this a little bit. Then I think we'll do one more. What's next? Do I have anything else on here? No. Can I just did this for you guys this weekend. So how about that, huh? I know. That's so nice. You want me to stand in front of it too?
Say cheese.
Okay. All right. So that's the same thing right here. So I want to look at overlap. Overlap is right here. And it is how much? 50 plus 25. Okay. All right, these are the things I said. I said, let me see. So this is 3. This is valve timing. From FAA book. From FAA. There we go. So we have the intake valve. Intake valve. And this is just an example of an engine. I don't know which engine it is specifically. I want to say, I thought it was, it's a Continental of some sort. I thought I wrote it down like, I think this is like an E225 or something like that. It's not important. The important part is it's just an example of an engine. It is not all aircraft engines are this way or all engines are this way. It's just one of them. Okay, so intake valve. So this particular one, it opens 50 degrees before top dead center. And this allows, this is what I really wanted to write for you. This allows use of low pressure created by escaping exhaust gases to pull in fuel air. So that's fuel / air. Also, this is FA. So FA. So you can do the same thing. FA mixture. So let's see. If valve opens too early, because too much of a good thing is a bad thing. So you're thinking, wow, if we open the intake valve a little early, why not just open it even more early? Well, the intake valve opens too early. Exhaust gases can flow backwards, can flow into the intake. So now we got gas temperatures exceeding 1500 degrees just went into your fuel air mixture. What happens then? Flow intake and ignite. What happens if we ignite all the fuel and air mixture in the intake system?
You'll be landing much sooner.
You get an indicator. There's an indicator.
Check engine light.
No. If it happens enough, yeah. Come on. It's an easy one. Backfire. It's called a backfire. It fired backwards. And all the fuel in the air ignites and it blows out your air cleaner. Whoosh. So that's a bad thing. Although I think I'd much rather have a backfire than an afterfire. A backfire is synonymous to a burp. An afterfire, it would be synonymous to a
Fire.
yes. Backfires in aircraft are terrible because it usually explodes out your muffler. And because your muffler is an integral part of your cabin heating system, it can often lead to death. I'll leave you with this little gem. I had to do my IA recurring training last week, which was so excellent. There was a lady who was an investigator for Piper, and she was just phenomenal. I'm like, oh my gosh. So one of the stories that she had was that it was a student pilot bought an airplane, put family members in the back seat. He's in the co-pilot. He hired a pilot to pilot the aircraft. So 4 people on board the Piper. They take off for, Thanksgiving Day thing going on across country. They take off, and shortly after takeoff, he calls in a mayday. The pilot had a heart attack and is unconscious.
Bro.
He's a student pilot. It's his airplane. He's somewhat familiar. I'm going to go to the nearest airport and land it. They have the ADSB of him going in circles, doing weird shit, and just plowing into the ground. So what happened? Autopsy report found that the pilot was incapacitated because of carbon monoxide poisoning. The co-pilot was nearly incapacitated, but had lost all faculties because of carbon monoxide poisoning. There were children in the back. The children in the back also died. They had less concentration. One of them was probably alive until the impact. Well, they're all alive into the impact, but one of them was conscious into the impact. But it was because possibly they had a backfire, blew a hole in the exhaust system. The exhaust system is part of the heating system. We take fresh air and we just run it across the muffler and then run it into the cabin. So if there's any cracks at all in the muffler, it is going to mix with that fresh air and go in the cabin. That's exactly what happened.
That's,
Yeah. And on that happy note,
you don't gotta go home, but you just gotta get.
don't go away mad. Just go away.